Ktoś tam jeszcze jest?
Będę się w przodzie, ale to nie bardziej jestem potrzebny.
So good afternoon, everyone. Today we're gonna listen about astrometric microlensing and surveys. So the talk will be given by Dr. Krzysztof Rybicki. Krzysztof graduated from this university, then he spent some years at the Weizmann Institute in Israel, working also on microlensing, astrometric microlensing, and now he's back working together with some people here on the topic. So the floor is yours.
Thank you. Thanks for having me here. As Milena said, I will say about the projects I've been working on recently, during the recent years. And all of them are kind of the same core of not only astrometric microlensing, but specifically they refer to astrometric microlensing as seen in surveys. So not in individual or follow-up observations, but more general and global approach. So it's especially important today, and this is well timed, I would say, effort, because this year, for example, we have two important events for the topic and for microlensing in general. And the end of the year, we have in September there is planned launch of Nancy Grace Roman telescope, and then later in December the release of the fourth release of Gaia data is planned, where also time series relevant for microlensing experiments will be published. Okay, so first I will start, bear with me for the first few slides about I will make sure that we are on the same page in terms of microlensing, and canonically I will start about scientific rationale behind the microlensing. So most importantly, or one of the most important science that stand behind microlensing is planetary science. Also historically it's dark matter. I will not really be touching with this subject from the top row. What I want to focus on is I think I will be just using this is the science related to stellar remnants, so mostly detecting black holes, neutron stars, and well, also white dwarfs. But the most important and the most interesting part from these three are stellar mass isolated black holes, which are very elusive objects that are difficult to detect without the use of microlensing. So microlensing itself, I will not go into the very basics, but just want to highlight the important problems that we face when studying this phenomena. So first is that the microlensing is very rare. That's why we need to observe a lot of stars at once, and this is how we really study microlensing with the use of dedicated surveys that are staring at the densest regions of the sky. So this is kind of already dealt with. And then the second problem, which is the core of why astrometric microlensing is so important in this branch, is that the standard microlensing, as we see here on this animation, doesn't really give a lot of information about the lens itself, about the physical parameters. So really the only thing we know that is related to important, interesting parameters is the time scale of the event, which is dependent on mass of the lens, its distance, distance to the source, and relative trajectories. All these parameters are kind of buried in the time scale, and these parameters are what we are actually after. To identify the lens, identify the object, we need to know, for example, its mass and distance to have idea what it is. So this is here. I'm showing the formula for the mass lens, and it is dependent on two observables that are not, and none of it is obtainable from normal light. So one of it is theta e, the time scale, the angular scale of the event, which is generally difficult to get. I will say about it more in a few slides. And another one is microlensing, so-called microlensing parallax. I will also say more about it later. It is sometimes available from the light curve alone, but and easier to measure than theta e, but it also requires some special circumstances to occur so that it's measured. So yes, so to say something about meaningful about the lens, we need to observe more effects on either on the light curve or something else. So first excuse me, first is the microlensing parallax. This it is related to the fact that the orbit, the Earth is orbiting the sun, and so because of its motion, we see different. We see the event from different perspectives during the motion of Earth around the sun, and thanks to this change of perspective, thanks to the projection of the acceleration vector on the plane of the sky, we see these wiggles that you see on the top, and thanks to this additional effect, we can infer some additional parameters. Now, to measure theta e, one of the ways to measure theta e is to observe finite source effect, but in practice, it's a rare effect. It requires very central passage of the source of the lens in front of the source, and thus for any population-wide studies, it's not very it's not really relevant. It also only allows us to study event by event more interesting, more special events. Another thing, can we remove this? Another thing is space parallax. I will not. I don't want to say a lot about it. Just want for clarity, I want to put it as yet another way of measuring pi e. So the parallax. It also, thanks to the fact that we observe a microlensing event from different perspectives, we can measure the parallax, which is related to geometric parallax. And the last one here is, well, we don't see it well, but at the bottom we see the yet another way of measuring theta e this time, which is interferometric measurements that allows us to separate the images, and thanks to that measure the angular scale of the event. And last one and most common ways of being able to measure theta e is to observe binary lensing event, where during the caustic crossing there is we can observe a finite source of the finite size of the source, and thanks to that also get a scale of the source plane and measure theta e. So I think this is the last one before the main actor today. So the last way of measuring theta E is thanks to the astrometric microlensing, which is really only the name for the effect that is always present during microlensing. So not only there is brightening of the source, but also it's the shift of its centroid, as we see on the top panel, the trajectory of the lens source relative to the lens, and the centroid is in blue. And then on the bottom we see relative trajectory of the centroid relative to the source position. So what is important here is that, first of all, I think I have it here as a summary, as a most important thing that we want to focus on that are happening during astrometric microlensing. So first of all, it's present in every event, and this is what we are actually after. We don't want to be able to measure theta E or other important parameters only for some selected sample of events. We want to do it as routinely as possible so that whenever we study populations, we can actually infer some statistically significant information. So it's very small. It's difficult to measure. It's the order of milliarc seconds, but then it's not as problematic as you would think, because the shape, as written here, is defined almost entirely by the light curve model. So if we know the photometric model, which is more easy to get, we know almost everything about the astrometric trajectory of the centroid. The only thing that we want from the astrometric data is the scaling by theta E. So the interplay between photometric and astrometric microlensing is very important. So to finish this lengthy introduction, as of today, the astrometric microlensing and generally measuring theta E is done mostly, or not general theta E, rather astrometric microlensing has been measured several times. These are the papers that I collected where theta E was actually measured thanks to, well, not only astrometric microlensing, it's kind of, I would call it positional measurements of theta E. I also included interferometry because it also has a means to measure theta E with positional measurements. But in all of these cases here, there are some issues that don't really allow us to study the population. For example, for HST, almost all the events that had successful measurements of positional shift, of centroid shifts, had something very specific about them. They were either very bright, very nearby. I think almost all of them had resolved lens and source. There is very limited number of such targets that are available for measurements. The only real astrometric microlensing was the black hole that the OAUW 110462 that has been detected using OAUW data, OAUW photometry, and HST astrometry. From adaptive optics, there are no detections as far as I know. Even though it looks promising, the nominal accuracy of adaptive optics, I would say, should allow milliarc seconds level accuracy, but there are no detections using these techniques. And then interferometry, as I said before, it's not really astrometric microlensing, but also requires very specific targets, very bright. The Gravity Plus project that will allow for more wide searches of targets might be available to, it might be possible to actually use it in broader searches, but it's still, I think, in the farther in the future than what I want to talk about. So these are the most important like takeaway messages from this introduction, let's say, that generally astrometric microlensing as it is now only allows for point kind of per event theta measurements. And well, the survey approach that I will be talking about in the next part is really the only way to reveal some population-wide information about the technical lenses, and this is where I will move to now. So first project that I want to talk about is the connection of the joint treatment of the OAUW data and Gaia data, which is, well, the idea itself is not very new, but also it is quite straightforward. We want to use Gaia astrometry mostly for theta E measurements, and we want to support it with all the information from photometry, which what OAUW provides. Very importantly, is not only precise, very accurately measured light curves and good models that allow for, as I'm showing here, the parallax measurements, but also a lot of additional information that we have from the thanks to the quality and history of OAUW data. So most importantly, for this project, we need very long baselines in terms of also photometry, which OAUW provides. First to have accurate models, as with any microlensing treatments, but also to, for example, to identify false positives and be generally sure that we are dealing with microlensing events. As I said before, the high cadence, which is for case of OAUW central fields, is several times per hour for the densest fields, which allow for accurate light curve coverage and recovering the parameters that are of interest, especially the microlensing parallax, and then the fact that, of course, the last point listed here, so the dedicated pipeline for crowded fields, I listed it here because it's kind of in contrast to what we can expect from Gaia data, which is by definition not performing very well in the dense fields. So the Gaia photometry alone is not really suitable for our purposes to join it with its astrometry. These are just fields of OAUW project. So in the plan, as I said, is relatively simple. What we want to do is collect all the possible OAUW, all the possible events that were detected by OAUW, and prepare the models for them, the photometric models, and then move to Gaia data. So the search we did was only for the years from 2010 to 2020, which is enough to overlap with Gaia data 4, data release 4, even though the Gaia itself was collecting data for 10 years, the fourth release is up until 2019, I think. So this is still longer than the Gaia baseline. And now in the search we used several steps to collect all the possible events. Maybe I will not go through all of them. The important part is that apart from the events detected in EWS, which is the system that is detecting and alerting the microlensing events kind of live, we found some additional events and also incorporated from other sub-surveys that were done within OAUW. The bottom line is that we are dealing roughly with 24.5 thousand events that will be the core of our sample in which we will look for black holes. Well, this is our final goal, but generally to study the Gaia data for that. So let me display everything. So in principle, the first you could think that the first step would be to filter these 25K events and find those that from which you would expect that they will actually the length be caused by the black hole lenses, which is roughly longer timescale. The timescale is proportional to square root of mass, so we expect statistically that longer events will have heavier lenses, preferably not blended, but this is also not necessary because not only the lens is not necessarily the only blend that is present. The microlensing parallax, as you see and might remember from the mass formula, is also the smaller the parallax we detect, the higher mass we expect. And then the last kind of cut that we might want to apply is on the brightness, which is, of course, in general in photometry, the brighter the event, the easier it is to measure. But for Gaia, it's critical because it has fixed. It is a scanning mission, so it has fixed exposure time. So these are this is a subsample of our events from OAUW on the pi-e-TE plane. So for which we measured parallaxes and we fit the parallax model. And I'm showing it just to visualize roughly how many interesting black holes candidates we can expect. And this is this lower right corner where I mark the events that we, under some assumptions about proper motion, we can expect a particular heavy lenses there. So this is just a small gallery of one of the longest events that we found. You see here both standard and parallax models fitted. So you see that some of the events span really multiple seasons, especially the top left one, where we have like 1, 2, 3, 4 seasons. The event was happening during 4 seasons, so the expected time scale is very large, probably a few hundred days, and then from them we expect also high mass lenses. Now, having a sample of light curves, we can move to preparing for Gaia data. We don't really have in hand the actual data, which will be released in December. But for the sake of first of detectability and second preparation for the data release, we of course need to perform some simulation and preparatory phase. So from Gaia, the important thing is first of all, it's not really It was not really designed for the astrometry, for the transient science, I would say. The main goal was the astrometric catalog. That's why the cadence that we have from Gaia is not suitable for coverage of photometric microlensing events. For astrometry, the situation is better because the timescale of astrometry is longer. Now the Gaia provides 1D measurements, which is kind of peculiar. I will explain it in the next slide. And importantly, of course, the main advantage of Gaia, its main characteristic, is that it provides high precision astrometric measurements. Now we can skip the way Gaia is scanning the sky. Maybe I will just quickly show what does it actually mean that Gaia provides one-dimensional measurements, because it might sound non-intuitive. So if we imagine that there is a normal star trajectory, so proper motion and parallactic motion, like you see on the left panel on the sky, what Gaia does, if we pick a few epochs or few epochs on this trajectory, the Gaia scans under the different angles. So these are these scanning directions, and then the actual shift from some average position can be plotted like this. This average position should be probably this is not actual average position of this particular event, but the point is that there is a reference position from which we can measure shift to the shift of each for each epoch of measurement. Now these are just shifted to the origin of the trajectory points, and then what is actually measured by Gaia are these projections of the shifts onto the scanning direction. So these things, sorry. So these red parts are, if we put it on the diagram, these are our actual signals for Gaia astrometry. Now, for example, you can see on the last point provides 0 signal, right? Even though the displacement is quite large, because the displacement is exactly perpendicular to the scanning direction. So in the end, this in the bottom right corner is roughly what we expect as a data product from Gaia. So this is the example of real data. It's a binary event, but it doesn't really matter. What I want to visualize here is that we actually already know that for Gaia, it is possible to actually measure these displacements. So the top panel here is a light curve, and the signal, this astrometric signal, this weird signal is in the middle panel. So you see the red and blue models, the red and blue lines are the model with and without microlensing, the astrometric microlensing, and you see that the red one from the residuals panel in the bottom, you see that the red one fits much better to the black points, which are the data points, than the non-lensing model. So having in one hand the oval photometry, and then being able to simulate the Gaia scanning angles and epochs, we are able to simulate the expected signal of the astrometric microlensing under the assumption of particular theta e. As I said at the beginning, the only thing we need apart from the photometric model is this theta e to have a complete on-sky trajectory of the centroid. And you see here on the plot the number of events that we expect for several levels of signal. Okay, so if we assume for our whole sample of 24,000 events, if we assume, for example, the Einstein radius of 5 milliards seconds, we expect, as you can see, for example, blue curve, we expect around 1,000 events that will be detected at the level of 5 sigma. And by the detection, I mean the difference between the substantial difference between the fit of standard astrometry, so proper motions, basically proper motions and zero positions, and model that does include lensing. So this is just a comparison of the number of events with this here with the cap on chi-square above 25. So this which translates to around 5 sigma level of detection. And if we also add the fact that we care for brighter events, we end up with roughly 7,000 events that are interesting sample for further analysis. So this is just example of one of the events. As you see again on the left side, the astrometric trajectory, this weird one-dimensional astrometry with residuals and cumulative chi-square plot that shows actually in this case quite strong signal, even though it's not really that well visible from the data itself. So that's it. This is the summary of this part. I will have to maybe quicken the pace. The important part for this experiment is that, as I listed here, we already did some preparatory work for the especially for the oval photometry selection and the initial detectability assessments. And then there are still some work to do, but we won't be able to prepare for everything. We need to see the actual Gaia data to for example, assess the level of systematic errors, which will be crucial in further inferences. So okay, the next step, which has its core in the use of astrometric microlensing as a survey, is related to KMT, which is another microlensing survey that is operating since 2016. Also with similar cadence to OAUW, including the fact that it has 3 telescopes. The cadence could be actually larger, and although it operates only from 2016, it's still enough for some astrometric signal, for example, of proper motions. So here the idea is also simple but slightly different than before. For KMT, we wanted to see if it will be possible to use just KMT data, both astrometry and photometry, to possibly detect some astrometric microlensing signal. So much more challenging, much less promising maybe because we have seeing limited data, but the idea is similar to what we had before. Now the first step was to actually retrieve the precise astrometry from the KMT events. I don't want to go into details. The main point is that what we did is first we worked not on whole images but only on cutouts or around the microlensing events detected by KMT, and that we did similar algorithm. We used similar algorithm to Gaia data and PSF fitting procedure instead of difference image analysis. So for dense fields like in the bulge, it's potentially problematic, but this is the more natural approach to astrometry, I would say. Now, let me skip this because it might be boring and it's not that relevant. The important part is that the proper motion precision that we achieved is between 0.1 and 0.3 arcsecond per year, and that even though for some fields it looks like we did reach the systematics level for the noise, but it looks like it will be possible to actually measure signal for some at least extreme events. Now these are two examples that I wanted to show you, which are probably not really astrometric microlensing, especially the first one on the left. You see astrometry in north and east direction and the light wave at the bottom. So both of them are of very high amplitudes compared to what we expect for the microlensing, because you see roughly 20 milliarcseconds. So it's most likely related to blending. This is at least what we suspect. But this is the main point I want to highlight really for this experiment is that it's not like with Gaia where you can kind of trust the astrometric measurements, because with the level of systematics that we expect from the seeing limited observations is much higher than for Gaia. So what we actually need is a proper assessment of detectability and treatment of potential false positives. So let me skip also that. Before going to Roman, I just want to show the plots of this detectability that we prepared for the when fitting the astrometric model with lensing and without lensing for a grid of different theta e, different Einstein radii, and angles of trajectory, which also impact the astrometric signal. So this is still ongoing work. That as you saw, there are some issues with the systematics, but we will be attempting to solve it. So the final part, which is only a few slides, is about the Nancy Grace-Roman telescope, for which the launch is planned for September this year. Now, in terms of the numbers, it's really the first space mission that will have dedicated microlensing surveys. So there are high hopes about this telescope. So especially because its field of view is 100 times larger than the field of view of Hubble telescope, and the expected accuracy is kind of the same, which paired with very high cadence leads us to those high expectations. So here I only prepared the very basic model simulations of what we could expect from Roman. As you see, the Roman has a peculiar cadence. Its observations will be divided into 3 seasons at the beginning of the 5 years mission, and then the 3 seasons at the end. So you see here on the plots the light curves in the top panels and the north and east directions of the astrometric signal. So even by eye, you can see that not only for extreme lenses like six solar mass black holes that is plotted on the right, but even for more common dwarf lenses, we should expect that if the assumptions about the precision is correct, we should expect that the astrometric signal will be detectable. So here are just the same signals but plot on the sky with both north and east directions, where one can tell that assuming only statistical error, the signal is clear. So, and just to compare this, this is the plot of this only black hole detected using astrometric microlensing. On the right, you see epochs collected by Hubble Space Telescope, and you see there are only like few of them compared to the number here. And this is just the projection of the relative accuracy of the mass measure of the theta e measurement, really, for different theta e values, and you can see that one can expect at least for brighter events 10% accuracy even for smaller theta e below 1 milliarc-second. And just to see the comparison between the expected Gaia accuracy, well, you don't really see the error bars, but you see the scatter, the Gaia error bars and rho. So this is a collection of less important facts and thoughts about astrometric microlensing in survey and in the context that I presented, but most importantly, the message that I wanted to leave are listed here, so that from the initial simulations, it looks like the OAUW and Gaia, the OAUW photometry and Gaia astrometry together will be able to will allow to explore dark channel population in a correct statistical way. That the seeing limited astrometry, so ground-based astrometry, is still possible, I think, at least to provide some limits. And And then for Roman space telescope, if there is no significant issues with the detector and statistical and systematic errors, it will be really a game changer for generally for microlensing. And that's it. Thank you. I'll take questions.
Thank you, Chris. Any questions, comments? Josh?
I have a question here. Thanks for the talk. I have a question concerning the microlensing parallax. As you were saying that, especially in case of Gaia data, we need the photometric model to get the astrometric prediction or astrometric model in general. And from the example you were only on the second on the slide, from the example that you showed, that you were selecting one of the OAUW events, the parallax model is this question.
You mean for one of the light curves, or
example on the end of the
one of these, or the
no on the one of the end of
this?
Yeah.
Yes, true. Yes, that's a good catch. It's so I would agree that if only from the light curve here, it looks like the parallax is not really constrained, right?
At all. Or
Or not constrained at all. But in fact, for this particular event, if you run more complicated fitting like MCMC, sometimes it's not constrained, right? So you can, so first thing is the difference between the standard model and the parallax model. They might be very similar, as you see here. And this is first thing. But the second thing is that how well it is actually constrained. So it's a question really on about the error bars of the parallax measurement. Usually it's not for a simple fitting procedure. You can get a lot of different values that will still lead for parallax that will still lead to the same standard like light curve. But for some cases, it will be actually well constrained, and simply the parallax close to zero will actually mean that it's very small. But it's true that sometimes it will not be constrained. Yeah, if you don't know the actual photometric model, so if you don't have well constrained parallax, you will not be able to predict that well the astrometric signal. Yes.
Yeah. And Neha?
Two questions. When you were talking about the event selection, you mentioned that it will have an intensity cut above average, and then you had a cut on the lens masses. So I have a question on both. Since you are dealing with different instruments, how do you want to define this average?
You mean?
The
average. So and what's the question about it? The
instruments are how do you find this average? Is dependent on which instrument you are dealing with. That is what I understand.
Well, this is one instrument. This is only for oval light curves. Yes. No, this is on for this experiment. We are only dealing photometry-wise. We are only dealing with oval light curves.
Fine. First, lens masses. 1.4 and 2.5.
Yes.
None,
0. No, actually, this is first of all, this is only for. So the significance is that, well, one is maximum mass of the white dwarf, and the other is, well, roughly at the neutron star limit mass. Not exactly, but doesn't matter. And so first of all, it's only for presentation purposes. We don't do cuts on them. And second of all, as you see, and that's the main point of this, they depend on proper motion. You can put this line to say, okay, roughly at this corner we expect heavy lenses, But the main point is that it is all degenerated, and you don't actually know what is the mass. It's not certain that the mass is high at the right corner, because the longer time scale can be not because of the higher mass of the lens, but because slower relative motion, for example.
What means PA, parallax, Earth parallax?
The E is what microlenses use this index for most of their parameters, and this is for Einstein, I would say.
Oh,
Yes, it's
Einstein parallax.
and the pi E.
No, after what is.
The pi E is actually the relative geometric parallax scaled by the Einstein radius. Okay, so it still has strong connection to actual parallax. Like this is the difference between lens parallax and source parallax, but it is in kind of in the units of Einstein radius.
Basically, it's called microlensing parallax.
Any more questions or comments? So I wanted to ask about the data policy of Raman, because we know how it works with OAUW, we know how it works with Gaia. It's, I guess it's.
I'm not sure. Well, for sure, it's open access.
So after
But-
some time, it's going to be released.
Yeah, but about the details, I'm not sure if there will be data releases every year. Maybe Radek knows more.
Yeah, I can comment on that. So the data will be published basically two days after they come to the ground. There's some pre-processing, and then the images and maybe even photometry is fully public. Everybody can use it as they want.
Okay, so there is like no priority for some given group of people working on that, which is good. Yeah. Okay, do we have someone from Zoom? I don't see. So thank you, Krzysztof. Hello. And with these great results, we are entering the semester break. And so we are meeting next semester, but the first seminar will be on March. I think it's 2nd or 3rd of March, because the week earlier, many people will be at the conference. So the second week of the next semester is a first seminar of the next semester. Thank you. Simple as that. Okay. Dziękujemy.
Dane z Romana będą publiczne, no chyba, że nie oddamy Grenlandii.